The other day, in section 5.8, we defined hyperbolic functions. Well, once we have hyperbolic functions, we also have inverse hyperbolic functions. Correct? All right, except we do need to be a little bit careful. Again, we have domain issues. If you look at your graphs, is hyperbolic sine a one-to-one function? Yes, because it passes the horizontal line test. So for hyperbolic sine, we don't have any domain and range issues. It's already a one-to-one function. How about hyperbolic cosine? It's not one-to-one. I do have a domain range issue. So for hyperbolic cosine, how are we going to have to limit our domain? From 0 to infinity. Yeah, your two choices are you either go 0 to infinity or negative infinity to 0. Everybody chooses to go 0 to infinity though. How come? We like positive numbers instead of negative numbers. And the same with some of the others. Some of the others are one-to-one. We don't have issues. Some are not one-to-one. Secant is the other one, which is not one-to-one. Correct.
What about, so for the cotangent lines, that's going to be, why is we select the domain range for that? The domain would have to be, can't be equal to 0, so it has to be greater than 0 to infinity, and the range would have to be outside of, is that positive one or negative one?
Yes. So what's going to happen with the inverse function, since the domain here is everything but 0, when you do the inverse function, the range will be everything except 0. And on this one, since the range is negative infinity to negative 1 and 1 to infinity, that will be the domain on the inverse function. The domain and range will switch. All right, looking back here. Oops, I didn't want to go that far back. We see that our hyperbolic functions were defined using ease. So what would you expect to find in the definition of your inverse hyperbolic function? Natural logs, because the inverse of ease is natural log. And that's exactly what you get. So let's see, where are they? Here they are. Here are your inverse hyperbolic functions. This is on page 387 of your book. So there's all the definitions.
So I have a quick question. Is the book you're using the one that Coin Community College provides that has all figure 1?
Yes.
Okay, so your page number's going on. Yeah, that'd be fine.
My page number should be exactly the same.
I was wondering.
The book that I have is not one of the custom editions, and it only covers Calc 1 and Calc 2. Page 387. I prefer this one because it has hardcover. It's going to last me longer. The ones with the soft cover, they get beat up pretty quickly. And I use them semester after semester after semester, so they don't last very long. So I like the hardcover one. That's why I have this one.
Do you teach Calc 3?
I have not taught Calc 3 in a long time, but I have taught it before. It's been, well, I haven't taught it since I've been here. And this is my 14th year here. So I did teach it where I was before. I taught it a couple times. So no, I don't teach Calc 3. My wife will torture you with Calc 3. And then you'll probably see me again for differential equations. I usually teach differential equations. Gansky. If I don't teach differential equations, my wife probably will. So we're the only two here who have taught it. So not to say nobody else could. It's a lot of work. Anyway, so there's our inverse.
They're like, you guys can have it.
Well, it's not a lot of work for me anymore because I've taught it many times. I've taught differential equations, well, not many. This is probably my 6th or 7th time teaching it. So when you've taught something 6 or 7 times, you got it pretty well figured out. But the first time you go to teach differential equations, it's a ton of work. The first time I taught it, I was a sabbatical replacement at a small 4-year college, and they were going to have me teach it in the fall. So I literally spent the summer reading the book and learning it, and I never took differential equations in college. So I had to read the book and learn it, and I did all the homework problems, and that's how I spent my summer. Good times, huh? All right, anyway. Here are our inverse hyperbolic functions. The nice thing is, we don't need any special rules for derivatives, do we? Because if I want to take the derivative of inverse hyperbolic sine, I can simply write it in its logarithmic form, and I know how to take the derivative of logarithmic things, don't I? Same with all of them. All of them are logarithms. I can take the derivative of all those. Well, there are formulas. Here they are. They work out fairly nicely. The derivative of inverse hyperbolic sine turns out to be u prime over square root of u squared plus 1. And the derivative of inverse hyperbolic cosine turns out to be u prime over square root of u squared minus 1. Do those look similar to anything we saw before? Yeah, they do. What do they look similar to? The regular old inverse functions. Yeah, what was the derivative of inverse sine? Well, I just used u, so it's 1 over square root of 1 minus x squared, correct? And the derivative of inverse cosine turned out to be the same thing, except I had a negative 1 on top. Okay? Compare that to the derivatives of hyperbolic ones. Very similar, right? They both have the square root. They both have the x squared, and the 1 is the difference of where the signs go. Okay? What's that? Right, because they have d dx of inverse hyperbolic sine of u. So they're giving you the chain rule version. So if this is just an x here, then it's going to be 1 over x squared plus 1. But if it's a 2x, then you have to use the chain rule, so you would have the derivative of 2x on top divided by 2x quantity squared plus 1. All right, the same thing with inverse tangent, inverse hyperbolic tangent. What was the derivative of inverse hyperbolic tangent? Well, no. What was the derivative of inverse tangent? U prime over 1 plus u squared. This is u prime over 1 minus u squared. Almost the same thing. Okay? And the other patterns follow also. So again, there's another strong relationship between the hyperbolic functions and the trig functions. Their inverses are similar, their derivatives are similar. And of course, once you have derivative formulas, you have integral formulas. The tan and the cotan turn out to be exactly the same. Yes, they do. Which is interesting.
So how do you know if you derive the answer back, whether the original answer is cotangent or tangent?
It wouldn't matter. They would be the same. They must differ by some sort of constant, though. That's all. Equivalent but not equal. Correct. Differ by a constant. All right, so notice how we write our integration formulas here. If we have du divided by square root of u squared plus a squared, for example, we could write that as hyperbolic sine inverse of au, but typically we don't. Typically when we take the antiderivative, we don't write it in the hyperbolic inverse form, we write it in the logarithmic form. Why? I don't know. That's just the way people have chosen to do it. So notice the plus 1, the formula with the plus, that would actually be inverse hyperbolic sine, and the one with the minus would actually be inverse hyperbolic cosine. And maybe that's why they just write them in this way. Then there's really only one formula. Your plus and your minus there is the same as your plus and your minus there. This one, a squared minus u squared on bottom, that would be your inverse hyperbolic tangent, usually written that way. And this one is your inverse hyperbolic secant or cosecant, depending on the plus or the minus sign. Questions about those? So what are you going to do with all those formulas? Those need to go on your next note card. Absolutely. Those formulas should all go on your next note card. One person in the class was very, very clever. Instead of writing these all down, either had access to a scanner or a Xerox machine which could shrink things. And so actually put the book there and shrunk it down and taped it onto the index card instead of having to actually rewrite it.
People like fold down or like fold it up.
No, you may not. Your surface area can be no more than the surface area of your index card.
Do the index card. For test number 1, fold up. Test number 2, fold down.
For final, cover the whole table.
I got it, guys.
No, your overall surface area can be no more than the surface area of your index card. But I thought that was pretty clever. They were shrunk and it was nice and neat and easy to read and didn't have to rewrite them all. Anyway. All right, so let's try some problems. Y equals hyperbolic tangent inverse of the square root of x.
Sorry, I'm just getting it now. Hyperbolic tangent inverse.
You got an abbreviation?
No.
There are abbreviations for those two. This one is quite often called cinch, and this one is called kosh. But I don't know that there's one for Tianhe. I don't know how you would make that one work. So you will hear that. You will hear those words, cinch and kosh. But I tend to just call them hyperbolic sine, hyperbolic cosine. All right. Anyway, we want to find the derivative. Y prime is. How do you find the derivative of that function? Well, you grab your formula card, right? And you look it up. So, for hyperbolic tangent inverse, we're going to have the derivative of the thing divided by 1 minus the thing squared. All right, so our thing is square root of x. So what's the derivative of square root of x? 1/2 x to the negative 1/2 divided by 1 minus the thing squared, x. So there it is. That's all there is to it. How about y equals hyperbolic secant inverse of the cosine of 2x. And it tells us 0 is less than x is less than pi over 4. Okay. What's that 0 is less than x is less than pi over 4 all about? It's your domain. Does it have anything to do with finding the derivative? No. But the domain of hyperbolic secant inverse is limited, so we just need to make sure we're plugging in the right kind of numbers. That's all they're telling you there. These are the numbers you can plug in. Has nothing to do with finding the derivative. All right, so y prime is going to be. I pull up my formula card. I look up the formula for derivative of hyperbolic secant inverse. I've got minus the derivative of the thing divided by the thing times the square root of 1 minus the thing squared. It's a lot to remember. All right, so I've got the derivative of the thing. What's the derivative of cosine 2x?
It's sine.
It's negative sign, but we already have a negative in our thing, right? So it's going to be 2 sine of 2x. The derivative of cosine is negative sign, but we already had a negative sign in our formula. And then we needed to use the chain rule there. The derivative of 2x is 2. Divided by, and then it was the thing, which is just cosine of 2x, times the square root of, I think it was 1 minus the thing squared. So 1 minus cosine squared 2x.
Minus the derivative of thing all over the thing times 1 minus the thing squared.
Yeah, I like to use technical terms like thing.
You can all identify it all the time.
It's easier than saying sine 2x over and over again. Cosine 2x.
Hyperbolic tangent inverse.
Yeah, see, it sounds impressive, doesn't it? What are you studying? Oh, I'm studying inverse hyperbolic tangent functions.
You know, I just come to this, a couple of those, you know, evaluate them to integrals.
Oh, some integrals? You want to do some integrals? Good idea.
You know he's going to do it anyway.
Yeah, it don't really matter. The mom's going to do it anyway. Integral of 1 over 2x square root of 1 minus 4x squared dx. 4x squared. Any ideas? Let u equal 2x. And why do you want to let u equal 2x? Because it looks like it's going to fit nicely, because this 2x will be our u. 4x squared is going to be u squared. The only thing I'm missing, I need du is 2 dx. So I need a 2 here, which means I need a 1/2 out front. Can't see out front. All right, so that becomes 1/2 integral 1 over u square root of 1 minus u squared. du. Thank you. I wrote dx. Bad boy. du. Equals. I flip the page back. All right, so notice that it best fits this one. So it's du over u square root of 1 minus u squared. So I'm going to use this formula. Although I heard you giving me an answer, and your answer was you were writing it in terms of inverse hyperbolics, which you could. You could write it that way. But again, traditionally, we write it in terms of LNs. So in this case, A is the number 1. So I'm going to have my negative, I'm going to have my 1/2. And then I'm going to have a negative sign and a 1 over A. But A is 1, so that's 1 over 1. Ln of A plus, so that's 1 plus square root of A squared minus U squared, or A squared plus U squared. Which one should I use? I should use the minus because I have the minus in my integral. So it should be 1 minus U squared. And then that gets divided by the absolute value of u. Plus c. Minus 1/2 natural log 1 plus the square root of 1 minus 4x squared divided by the absolute value of 2x plus c. Why do you need the absolute value sign?
No, why don't you with that one?
Because x has already been
because the square root thing's always going to be positive. So 1 plus that thing's going to be positive. And so we really only need the absolute value signs around the 2x, because that's the only one that could be negative. It would not be wrong to put absolute values around the whole thing. You really only need them on the bottom. Other questions? So you have to be very careful of your formulas. If this turned out to be u square root of u squared minus 1, we'd have a different answer. What would it be if it was u square root of u squared minus 1? No. I'll give you a hint. It's not any of those. Any of those, I mean. It would be arc secant. Correct. So you need to be careful. Our inverse formulas look an awful lot like our other inverse formulas. It depends on the placements of the minuses and where things are. So you might want to have both of them on your next note card. Correct. Because either one of them could show up. Depends how I place the minus sign. All right, let's try another one. How about the integral of x over 9 minus x to the fourth dx. X over 9 minus x to the fourth. Any suggestions? U equals x squared. That seems like an interesting idea. Why do you think u should be x squared? The x to the fourth can be u squared, and all of our formulas have u squareds in them. And when I take the derivative, I'm going to get that x right there to go away. So du is 2x dx. So I can put a 2 there and a 1/2 there. 1/2 integral 1 over 9 minus u squared du. We look up our formulas. That one's an inverse hyperbolic tangent, but we don't usually write it that way. We usually write it this way, using the LMs. So in this case, we have 9 minus u squared, so a is the number.
Question.
Go ahead.
Would we get points off if we wrote it in the inverse tangent?
No, you would not. If you wrote it using inverse hyperbolic tangent, that would be fine. A is 3. So this is going to be 1/6 ln of a plus u. So that's 3 plus u over 3 minus u plus c. Okay.
Do you have to pull out a 1/2 to the 2x dx? So 1/12?
Oh, I'm missing a 1/2, aren't I? Right, because I should have 1 over 2a. That's 1/6 right there. But then I have another 1/2 over there, don't I? Yeah, I forgot a 1/2. We can sneak that right in there. Thank you. 1/12 ln 3 plus x squared divided by 3 minus x squared plus c. Other questions? All right. Two problems for you to try. Number 80 and 82.